Hello everybody, this video is about the binomial theorem, and it's all about expanding complicated expressions. Now you would have expanded something like x plus 2 all squared before. It got x squared plus 4x plus 4. There's a little shortcut rule for doing that, or you might have done in the past x plus 2, and multiplied everything out like that. End up with your answer there. That's okay for something simple like x plus 2 squared. But what about if we had, say, x plus 3 to the power of 4? It'd be very painstaking to go x plus 3 times x plus 3 times x plus 3 times x plus 3. By the time we multiplied all those out, it would take a long time. We'd still probably get the right answer if we did it carefully, but we probably need a quicker way, without a calculator of course, to expand something like x plus 3 to the power of 4, or even more complicated things like 2x plus 7 to the power of 5, for example. So we need a way of being able to do those complex expressions. Alrighty. Now, to expand complex expressions, first of all we need some understanding of something called Pascal's Triangle, okay, which is here, and you might have seen before. It's often used in things like probability as well. So Pascal's Triangle, you don't really have to memorise it because you can always generate the next line from the line before. As you can see, hopefully, the numbers below, it's like 5 there, is generated by adding 1 and 4 together, the number above it. The number 10 here is generated by adding 4 and 6 together, the numbers above it. 6 plus 4 equals 10, the number below. 4 plus 1 equals 5, the number below. So if we were to generate the next line here, that'd be quite straightforward. It would be 1, 6, 15, 20, 15, 6, and 1 on the end. And then the next line would be 1, 7, 21, 35, 35, 21, 7, and 1. So each time there, to generate the number below, I've added the two numbers above. So we can keep on going, get a massive triangle. So that's Pascal's triangle. Now, how do we use this in practice? Well, when we're expanding, and you can see here along the side, it's got some expansions here to the power of 0, to the power of 1, to the power of 2, etc. We use these numbers in Pascal's triangle depending on what we're raising to the power of. So you'll see in a moment that if we're raising something to the power of 5, we use the line of Pascal's triangle in which the second line is 5. Sorry, the second number is 5. If we're raising to the power of 3, we'd use the line on Pascal's triangle where the second number in, from the left or the right, is 3. If we're raising to the power of 7, we use this line, the second number there is 7, and so on. Now those numbers on Pascal's triangle can be labelled in the following way. When you do combinations, there's a thing called NCR. Okay, and for example, you might have 4C2. Now 4C2 corresponds to the third number in, here it is, on the fourth line, sorry, actually the fifth line of Pascal's triangle. Okay, that's 4C2. This would be 4C3, this would be 4C4, this would be 4C1, this would be 4C2. Okay, and going back to the previous slide, they correspond to those numbers. So 4C1 is 1, oops, just change colour here. 4C1 That should be 4C0, sorry. Let's go back a minute. Change that to should be 4C0. Okay, so 4C0 is 1, 4C1 is 2, 4C2, no it's not. 4C1 is 4, 4C2 is 6, 4C3 is 4, and 4C4 is 1. Okay, so we can label any of these. This last line here, this one here would be 7C0, 7C1, etc., etc. Cross to 7C7. So that's how we label the numbers on Pascal's triangle. Alright, now you can actually work those out. I usually just use Pascal's triangle, but you can actually calculate any of these. If you've got 4C2, there's a little formula here. If I just get rid of that for a moment. See the formula here for working it out. So 4C2, for example, using this formula here, would be, it would equal 4 factorial over n minus r, so that's n and that's r, so 4 minus 2 would be 2 factorial times r, okay, which is 2. Now we used to use that, but the course now means that we don't really have to work out these anymore using that formula. So just take note that you can find out what 4C1, 4C2, etc. is from using Pascal's triangle. Alright, here's all the complicated theory to do with binomial expansion. Okay, and here's the key formula here, like so. What I'm going to do first of all, instead of worrying about all that, which can look quite complex, is actually do a question. Let's expand 2x minus 3 to the power of 4. Now, as soon as I see that it's raised to the power of 4, I automatically focus on this line of Pascal's triangle, the one that has 4 second from the left or second from the right. So they're going to be my coefficients. Okay, so I'm just going to get, so we'll just memorise those. So that's 1, 4, 6, 4, 1. Okay, and from the Pascal's triangle. And first thing we're going to do is write those coefficients down. Okay, so it's going to be 1. Just turn it back to black pen. 1, 4, 6, 4, 1. In fact, I might just give myself a bit more room there, because I don't think I'm going to be able to fit all that in. There we go. 4, 6, 4, 1. Okay, so they're going to be my coefficients. Now, this equates to 4C0, 4C1, 4C2, 4C3, and 4C4. Okay, so they're the coefficients I'm going to use. Now, to apply the binomial theorem, which I showed you back here, it's just quite complicated here, in that green box, is that I'm going to write down this step, which I probably don't need to write down, but I'm going to because it's our first example. So it's 4C0, then it's in my first term raised to the power of 4, the highest power. Then the second term, negative 3, raised to the power of 0. Okay? And that one's always 0, that first one. Plus 4C1, 2x to the power of 3, negative 3 to the power of 1. You'll see a pattern develop here. Plus 4C2, 2x to the power of 2, minus 3 to the power of 2. Plus 4C3, 2x to the power of, I've got to be careful here, 2x to the power of 1, negative 3 to the power of 3, plus 4C4, 2x to the power of 0. I'm just going to run out of room here. Negative 3 to the power of 4. Just squeezed it in. Okay, so I'll just tidy that up a bit. Okay, so you can see there, my coefficients out the front are these numbers here, 4c0, 4c1, 4c2, etc. I've got two terms, I've got 2x and I've got negative 3. There they are. I go up, sorry, with the first one, I go down a power each time. So I go from 4 to 3 to 2 to 1 to 0. And with my other term, my negative 3, I go up each time from 0 to 1 to 2 to 3 to 4. Okay, so you can see there how things are working. Alright, now I'm going to, instead of having 4c0, 4c1, etc., put the actual numbers. So we know that 4c0 is 1, 4c1 is 4, etc., etc., etc. Okay? So, here instead of 4c0, so I'm doing the next line now, equals 1 times, we've got 2x to the power of, 2x raised to the power of 4. So it's going to be 16 x to the power of 4. Negative 3 to the power of 0 is 1. Okay, so I've done each of those there. That's 1, and expand the brackets, it's 16x to the power of 4. Right, so we've dealt with that one there. Now let's look at this one here. So it's plus 4c1 is 4, 2x raised to the power of 3. I need to be careful of this guy here. Okay, 2x raised to the power of 3 is going to be 8x. Oops, 8x cubed. And negative 3 to the power of 1 is itself negative 3. Plus, let's look at the third term now. 4c2 is 6 multiplied by 2x all squared is 4x squared. Negative 3 squared is negative 3 times negative 3. So remember, a negative times a negative equals a positive. So negative 3 squared is 9. Plus, we're now up to the fourth term here. 4c3 is 4. 2x to the power of 1 is 2x. Negative 3 cubed is negative 27. Because remember, negative 3 times negative 3 times negative 3. Negative times negative times negative is negative. 3 times 3 times 3 is negative 27. Alright, that's there as well. Last term, 4c4 is 1. Plus 1 times 2x to the power of 0. Anything to the power of 0, anything in brackets, doesn't matter what the bracket is, to the power of 0 equals 1. So 2x to the power of 0 is also 1. Negative 3 to the power of 4. There it is there. Negative 3 times negative 3 times negative 3 times negative 3 is 81. Alright. Just now have to simplify everything and we've got to our answer. Equals 16x to the power of 4. Done that one. 4 times 8 is 32. Times another 3, negative 3, is negative 96. X to the power of 3. Okay, so we've got 6 times 4 is 24. 24 times 9 is 216, so it's plus 216 x squared. So we've done that one there now. Done those three. Fourth term, 4 times 2 is 8. 8 times 27 is, let me see, 216 as well, I think. Yep. So we've got minus 216x, because a positive times a negative is a negative. And 1 times 81 is plus 81. So there's our first expansion in the binomial theorem. So that should get us started. So just to summarise then, we can use the numbers in the Pascals triangle as our coefficients for expanding. So in other words, if I set you the question 2x plus say 7 to the power of 5, we would use this set of coefficients here. Okay, so the first term would be the first coefficient, so 1 multiplied by the first term, which is 2x to the power of 5, 7 to the power of 0. Okay, so you start with power of 5, the highest power, the lowest power 0, then plus, next coefficient is 5, as we move along, 2x, and remember that one's 5c1, so 1 was 5c0, this one's 5c1, then 2x to the power of 4, 7 to the power of 1. And across we go, we use these coefficients every time. The powers of 2x decrease, the powers of 7, positive 7 increase along the way, and then we have to simplify at the end. Okay, probably could do some problems from the book if you're brave enough after watching this. If not, you can wait till class. But we're looking at exercise 1A here, and you could probably have a go at exercise 1A, number 1. That's all for now.